Welcome to Northern Colorado Amateur Radio Club. To all new hams, this is Kilo Fox Zero, Colorado Boy.
I am Chris, AE5IT, and I'm going to be talking about impedance matching and understanding what exactly that means, what an impedance mismatch is, what's a standing wave ratio, hopefully dispelling a few myths and hopefully showing you guys something really cool about how easy and actually fun it is to play with this stuff and watch what's going on here. There's a lot of mystique and myth around SWR. If you want to go on to the next slide, please. So we hear a lot of times, my antenna is useless above, it's useless on that band because my SWR is above 1.5, or maybe it's above 2 to 1, or maybe it's above 3 to 1, or whatever number somebody happens to be throwing out there. Like, oh, my system's useless because my SWR is too high. Well, maybe, but maybe not. We also hear things like antenna tuners will only make your transmitter happy. Well, they might make your transmitter happy, but there's actually a good bit more going on. So go on to the next one. So there's, when we talk about standing wave ratio, we need to understand something about what goes wave mechanics. Waves behave the same in just about every medium, whether that's sound waves or waves in water, or guitar strings, or radio waves on a coax line or on open feed line. So if you think about, one of the things that's really important is any two waves in a medium, when they intersect, they will sum together. So in this case, we've got this red signal here. It's at some fundamental, whatever. We've got this other signal that's on the same line at the same time, and it's the fourth harmonic, or it could be anything really, but in this case we've got a fundamental and we've got its fourth harmonic. If you were to measure the voltage on the line, you would see not the fundamental signal, not the fourth harmonic, you would see the mathematic sum of the two of them together.
This question, excuse me for interrupting, but I think you need to define what your x-axis is that we're looking at here.
So if you wanted, you could think of this as a physical line. So we've taken a snapshot in time. You've got signals traveling down the line at the speed of light.
Because sometimes that axis is time.
It actually works either way, but yeah, it's.
And so just to be clear, this is distance that we're looking at here.
We can think of it as distance, absolutely. This does work either way, but yeah, in this case, think of it as distance. So this is called superposition. These two waves existing on the line at the same time will add together. They won't mess with each other necessarily. You'll still have the individual signals if you can split them out with, say, a duplexer or whatever. But if you were to measure the signal on the line, you're going to see the sum of them. Let's go on to the next one. So if you have two signals moving in opposite directions, they're the same signal. Let's say they're the same phase, same frequency, or sorry, no, forget phase. Same frequency, same amplitude, but they're going in opposite directions. So we've got this red signal moving forward, and we've got this blue signal moving backwards. Those are going to add together on the line. And if you were to come in and measure the voltage at different places on the line, you're not going to see either of those individual signals. You're going to see how they add together. And in this special case of identical signals traveling in opposite directions, you will get a standing wave. As they travel through each other, every once in a while they'll sum out totally. You'll see sometimes this purple line is just flat. You'll see no signal on the line if you were to measure it at that moment. But a half cycle later, you're going to see the peaks add together to a big peak. You're going to see the troughs add together to a big trough. So that's your standing wave. And if you notice, this standing wave, the reason they call it standing, it's not moving at all. It's just flipping up and down. You might, if you were to look at this, if you could see the radio waves doing this, you might not even know that something was actually moving through this. but you do have a signal going forward and a signal going backwards. Let's go on to the next one. And something that's important to note is that that summed signal, that standing wave, it will trace an envelope. Similar to if you're looking at a voice AM or sideband signal on an oscilloscope, you'll see the envelope, right? We have an envelope here. And this is the maximum voltage you'll measure on the line. This is the minimum voltage. That's going to become important in a moment. Click on to the next one. In fact, here it is. This is how we measure standing wave ratio. One of the ways we measure standing wave ratio. If we were to go and measure the voltage on the line, and we found what's the maximum, what's the minimum, we divide them. We have two 1 volt signals going in opposite directions. When they meet, they sum up to 2 volts. So our voltage max is 2 volts. Voltage minimum, 0, because as they're passing through, when you have the red signal at 1 volt and the blue signal at -1, they sum to 0. So your voltage minimum, 0. Standing wave ratio is infinite here. Because 2 divided by 0, well, you can't do that, infinite. Okay, go on to the next one. So we have another special case, same frequency, same speed of propagation, they're both going the speed of light. They're going in opposite directions, but the amplitudes are different. So we have a 1 volt signal going forward, but the return signal is only a ½ volt. So what we'll see, you look at the purple line, that's the sum, and the green is the envelope that the standing wave traces out. And this looks really funny, but this is exactly what you get on the line. And if you measure your voltage max, you'll get a 1.5 volts. Click on to the next one. So you've got a ½ volt peak and a 1 volt peak. That's 1.5 volts, right? That's your Vmax. Your Vmin is the peak of this one and the trough of this one. When those happen to line up, so you'll get ½ volt. And your standing wave ratio, 3:1. Okay, click on to the next one. And if we had only a forward signal and nothing getting returned, you don't have a signal going backwards, only the forward. Well, in that case, the red of your forward signal and the purple of your sum are the same thing, because you're adding the forward signal to nothing. So the red is hiding underneath the purple here. And then your envelope is just this flat block. Your voltage maximum and your voltage minimum are identical. And you've got a 1:1 standing wave ratio. All right, so that's kind of a demonstration of what's happening on the line. If we click on to the next one, where do these reverse signals come from? It's easy to think about the forward signal. That's what we're transmitting out of our FT817 here, which is not on the right frequency. So we've got our forward signal coming out of our transmitter, but this reverse signal, where's that coming from? If we have an impedance mismatch somewhere in the line, so we've got a piece of coax or our open wire line or whatever, and it comes up to some point, and let's say this open wire line is 200 ohms characteristic. It's coming up and then it hits an antenna that's, say, it's just a dipole. Let's say it's 73 ohms. Well, that's a pretty big mismatch. So when you have that impedance bump, the power can't all get through. And some of it gets reflected back. Some of it goes out, but not all. So when people talk about their SWR is high, part of what's happening there, their signal's going forward and not all of it's getting radiated out. Asterisk, we're going to come back to that. And this is the same thing in all other kinds of waves. You think of a tsunami, right? There's an earthquake somewhere and now there's this ripple moving across the Pacific Ocean. Well, the ripple out in the middle of the ocean isn't very big because all the power of that wave is spread through the entire depth of the ocean. But when it comes up on shore, as the bottom of the ocean gradually gets shallower and shallower, right, it transforms the power of that wave into something that ends up being very big and very powerful and can get up onto the shore. Whereas if that same pulse, that ripple were coming through the ocean and it suddenly just hit a cliff, you'll never even notice it. It's because it just all gets reflected. It cannot get transformed into working on the, even if the cliff is just right there at sea level, you're not really going to see much happen. Because this, you've got this, the impedance of the ocean, and the depth is a big part of that, of this wave traveling, and then suddenly the depth of the ocean changes. The impedance of the ocean changes, and that wave just kicks right back. So these reflections, anytime you have a change in the behavior, the physical nature of your medium, whether that's water, radio wave, the air, your transmission line, anytime you have a sudden change, you're going to have a reflection. So what can we do about that reflection? We want to transform it, like the ocean getting shallower. Let's click on to the next one. So there are these 4 ways to determine your SWR. We talked about one of them, the maximum voltage on the line, the minimum voltage on the line, and you just divide them. It's your voltage standing wave ratio. You can do the same thing with current. If you measure your maximum current and your minimum current, usually it's easier to measure voltage, but if you can do current, you can get the same result. If you have a power meter, and this is what most of your SWR meters on your bench do. Most of your SWR meters are actually bidirectional power meters. They're measuring the forward power and the reflected power on the line at that point, and that's important. They only know what's happening right there on that point in the line. Once you have those 2 measurements, you can do this math, and you have your SWR. It all works out the same. And then if you know the characteristic impedance of your line, 200 ohms here, and you know the impedance of your load, such as a dipole at 73 ohms, you can divide those, and again, you get your SWR. You can just do whichever of these is the easiest to measure for what you're doing right then. They all give you the same answer, but especially with the power meters, it's really important to understand what you're actually getting.
Question, excuse me.
Yes?
Our standard meters at home, which of those formulas do they usually measure? Our SWR bridge at home?
They'll usually be measuring your, almost always, they're going to measure your forward and reflected power. And they'll do analog circuitry tricks. If you have one needle that goes to a certain point, it's just analog circuitry tricks to do that for you. And if you have the cross needles, they just balance the ballistics of the needles in such a way to make it land in the right spot. All right, let's click on to the next. So what does this mean for us in radio? We've talked about impedance mismatches, we talked about transformation, we talked about reflections. Click on to the next one. We have here this open transmission line demo. I've got an FT817 on 2 meters. It'll be on 2 meters here in just a second. All right, so we've got an FT817 on 2 meters. It is putting a ½ watt. Yeah, it's putting a ½ watt onto this line, 50 ohms out. We have here a 4-to-1 balun. So it comes from 50 ohms unbalanced, goes through this little device, comes out 200 ohms balanced. Then it connects into this 200 ohm balanced line.
Russ, in the back row, there are 2 wires there?
Yeah, so there's 2 pieces of hobby tubing, just 1/4 inch brass rod. Yep, and they're spaced 1/3 of an inch apart on center. And you do the math, and that's 200 ohms characteristic. So this gives us direct access to the signals that are going to be traveling through this line. With coax, coax is nice, it's convenient, but we don't have access to the signals. Here, we can mess with them, we can see them. We're going to do that.
And what's at the other end here?
At the other end here is just a way for me to connect antennas. So I've got this little stubby, just whatever piece of scrap brass I had, kind of a dipole, and then I can slide different linked elements onto it to get different size. So this piece of brass rod will just slide on.
The first piece you had there, is it insulated in the center? So
It is insulated in the
so
center,
we're actually
yeah.
doing a dipole, okay.
Yep.
I saw one physical thing.
Yeah, there's just 2 little L pieces zip tied to a piece of wood. Okay, so we also, in this setup, we have some directional power indicators right here. And what this is going to do for us is, as we transmit power down the line, this will light up for the power going in one direction, but not the other. So we'll be able to see forward power and reverse power. This is just a directional coupler with an LED. So power going in one direction will light up the LED, the other gets burned up into a resistor. And that directional coupler is what's happening inside your SWR meter on your bench.
So we have two wires, one from the meter and one from the antenna near each other. So I think of that as a transformer. Well, how we transmitting energy into the LED?
Oh, okay.
That's the part I never understood of an SWR.
So if I just take these two pieces of brass and I hold them pretty close to the others, they'll couple. They will capacitively couple. And so we'll have voltages, we'll have power flowing through these, even though they're not touching. They're just getting kind of close. This is the same way you get crosstalk between circuits on your motherboard at home or whatever. So we also have some voltage indicators. This is not directional, but this will couple to a high voltage point on the line, and the LED will come on. And it'll vary in brightness depending on the voltage on the line at a given point. And then I've got various ways that I can mess with this antenna system. I've got a dummy load, I've got a short circuit, and I can open circuit it. So we're going to have some fun here. Let's go on to the next slide, please. Okay, so let's look at a matched condition. This is about a 200 ohm line. I have just under a half watt's worth of, or just over a half watt's worth of resistors here at 200 ohms. And I'm going to key up. So I'm on the right frequency. I key up at a half watt here. And SWR meter, I know you guys can't see this, but the SWR meter on the front of my transmitter, not complaining at all. It sees a perfect matched load. So if I take my directional power couplers and I put them on the line, because there's a matched load, there should be no reflected power. That dummy load should be absorbing the whole half watt. So now I have a half watt going forward, and we should see the forward power indicator light up, but not the reverse power indicator. And there it is. I know it's kind of bright in this room, and the LEDs are kind of dim. I don't know if everybody can see that. But sure enough, we have the forward power indicator lighting up, and the reverse is not. And just to show you it's not a trick for where it is on the line, same thing. So we have a half watt going forward, nothing coming back because it's all getting soaked up by that dummy load.
Your two little toys on there, if you physically rotated 180 degrees, they change names? Or what?
Well, so they would still, the thing is I would be able to see them and you wouldn't because the LEDs are directional. So, but they would change direction, but you guys wouldn't be able to see it either way. So that's why these are assigned to a certain direction. Okay, let's go on to the next slide. So we had forward power, no meaningful return power. So an open circuit. So my open wire lines just go nowhere. And I transmit, and my SWR meter on the front of the transmitter is very unhappy. It is pegged all the way to the right. So let's see what that looks like on the line. So I'm just going to drop the directional indicators on here. And we have a whole bunch of forward power and a whole bunch of return power. Get these a little closer to each other where you guys can hopefully see them. So those are both pretty bright. So what's happening? We have power going forward, and it can't go anywhere. It hits this spot, and 100% gets reflected back. And it just sits here and bounces back and forth in the line until it burns up as heat. And most of that's going to burn up in the coax, because coax is lossy, this isn't. But it's only a half watt, so we won't notice a whole bunch. So we've got our voltage indicators. I'm going to drop a couple along the line, and we're going to see how they light up. Anybody have a prediction about what we're going to see here with these voltage indicators? Which ones are going to come on bright, which ones aren't going to come on at all? Pardon? Nothing yet. I haven't transmitted. Yeah, so it's on an open, and I'm not transmitting. So the open will be bright, and sure enough, there it is. So the open's lit up, and we're also lit up again here. Why is that? Half wavelength away, exactly. So remember with that animation earlier, we saw high, low, high. That repeats every half wavelength. And that also means it inverts every quarter wavelength. Here's my handy dandy meter stick. This is why I use 2 meters. My meter stick gives me a half wavelength away. We're pretty bright there. We're pretty bright there. And then here, right in the middle, we're not coming on at all. And there is some mechanical slop, but as I move around, like I cannot get this one to light up. Lights up here, not there. Right? So we have infinite impedance right here. This signal cannot get across this open. You can have as many volts as you want across an open until your dielectric breaks down. So we have a high voltage point here. Half a wavelength away, 1 meter away, we have another high voltage point. A quarter wavelength will have a high current point. The power here isn't enough. I wasn't able to successfully build current indicators for a half-watt system. The guy that there's another presentation by a guy named Bill Hayes out of, I think, Atlanta. And when he does a presentation like this, that this was heavily inspired by, he runs 40 watts. He uses incandescent bulbs, and he sets off car alarms in the parking lot. Speaking of which, AE5IT. So, because we are transmitting here. Okay, so let's go to the next slide. And so, all right, so let me throw a short circuit on there and let's see what that does. Anybody have a prediction what we're going to see differently? Yep, everything, exactly, you're both right. We're going to see 0 volts on the end. This will not come on. And that whole pattern of standing waves will shift over a quarter wave, 90 degrees. All right, so here we go. We're transmitting. Here at the end, at the short circuit, we've got nothing. Here at, again, we've got a little mechanical slop, so it's hard to get this one to light up all the way, but it is on. So here we are at a quarter wave. We're bright. If I come about, so half wave, and then come back here and do it again, and we're bright again. So here's my voltage indicator at a half wavelength. It's not on. And if we had a sensitive enough system, we would see this gradually get bright and drop back down again. And I do apologize how bright it is in this room and how dim these are. I know it's hard for everyone to see. I hope not impossible. Okay, and again, we have the same standing wave ratio of infinite, right? Because of the short circuit, everything is getting reflected back. You just have a phase shift. So my standing wave, my SWR meter on the transmitter is just as unhappy with a short as it was with an open. All right, now let's click on. All right, so we're going to put a dipole on this. Just a regular 2-meter dipole that you might build at home. No tricks here. This is just a dipole. So we're looking at about 73-ish ohms. It's not going to be exactly that. There's a bunch of metal in the near field. I'm walking around in it, whatever. Okay, so when I transmit, AE5IT, SWR indicator is a little unhappy. Power, forward and reverse power, we're going to show, I predict, we'll show a lot of forward power and a little bit return. I'll find a better spot on the line. There we go. So hopefully you guys can see this. The forward power indicator is pretty bright. The reverse indicator it's lit up. It's not crazy bright, but it is coming on. So we've got a whole bunch of power going forward and a little bit coming back. It looks a lot like one of our animations we looked at earlier, right? The one where we had the envelope like this. we're looking at about a 3-to-1 SWR here with this 200 ohm line and a 75 ohm-ish dipole. So we saw some reflected power. Let's look at our voltage indicators. I'm just going to sprinkle some along the first half wavelength and see what we come up with. So not a whole lot of high voltage on this line. So our standing wave isn't going to be too bad. Whatever. We don't have like really high voltage points on here, but we do know we've got about a 3-to-1. It has to be about a 3-to-1, based on the impedance, the characteristic impedances of the line and the load. And then we saw, if we can imagine that one of these is about 3 times as bright as the other. Sure, that feels about right. And I don't have my receiver set up. Crap. So I'm going to take a moment to do this because it'll get more important here in a moment. I've got a spectrum analyzer running on the laptop there. Let me throw. Apologize for the delays here. All right, so what we're going to see here in just a second, as we change the loads around, we're going to see what that does to the receiver and the signal strength that it sees. If you Alt-Tab over to that other window, yeah, that's the one. Okay, let's get kind of a baseline here. Can you click that button right close to the, yeah.
And what is that program?
This is GQRX. Oh, this is just a general purpose spectrum analyzer. All right, well, I'm not going to diagnose technology problems right now. Thank you. We'll just skip it. So back to the slides. So I'll just tell you what you would have seen if that were working. Okay. So even with this 3-to-1 mismatch, we'd be seeing a pretty good signal. I mean, of course, we're only like 20 feet away, whatever, if that. But we would see some received signal, right? We'll just call that we'll call that baseline. It's not like nothing's getting out, right? We're getting some out, and you'd see it at the receiver. Let's click on to the next slide. Okay, so let's do another really bad mismatch. That was 3-to-1. So I'm going to put a full wave dipole on here, right? So this is like we're feeding an antenna at its second harmonic, right? So that's, you're not supposed to do that. You're feeding it at a high voltage point. It's not going to work. Nothing's going to be happy, blah, blah, blah. And sure enough, we're going to see a really high standing wave ratio. Should be about 12-to-1. All right, so I transmit here, AE5IT. And if I can find a good spot for it to couple. All right, so here's forward power and here's reverse power, and they're both really bright. So if we've got about a 12-to-1 SWR, right, that's pretty bad. Not a lot of the power that we're transmitting is immediately going out of the antenna. A lot of it's getting reflected back and just bounces back and forth. But here's the thing. If we had our receiver working, you would see that the received signal is not actually all that different. It's just a couple dB off. Even though this is a really bad antenna, we're feeding it at a high voltage point. We have a huge SWR here, but everyone complains about high SWR. So what's weird? Why would it receive just as well? Anybody have any theories? So what's happening is our open line here is really low loss. So yes, a lot of the power, most of the power is reflecting back. But it hits this point and it just reflects back again. and it bounces back and forth, and every time it hits this, say 30% of that pulse gets radiated out. The other 70 comes back, but then it just comes right back again, and it has another chance, right? So most of it gets radiated because this is so low loss that you don't actually lose a lot to heat. So when but most of us run coax, right? And coax is lossy. So when you're running coax from your transmitter to your antenna, to right up to your antenna, if you have a high SWR, that stuff that's bouncing back gets turned into heat. The birds that come and rest on your coax line, the worms that crawl around it on the ground, they're getting warmed up. You're making them a nice little resistive heater, and your signal's not getting out. That's when SWR is bad for your transmission and for your receive as well. Let's click on over. So yeah, the 3-to-1 SWR and the 12-to-1 SWR didn't really look that different on the receiver, which unfortunately I can't show you. Let's click on. Yeah, and again, so we've covered all this. Open wire line, high SWR, who cares? It works fine. Now, can we make it better? I say yes, we can. If we can transform, if we can put an antenna match, we can put an antenna tuner on this line, we can actually make that a little bit better. So if we put, I did the math ahead of time, if we put a 4.7 picofarad capacitor 23 centimeters from the load, which is this guy, it's for the other antenna. So with a half-wave dipole, that's the 3-to-1 SWR. I take my little shunt capacitor and I put them about 23 centimeters back. And I move these because I don't want to make reflectors, right? That's a Yagi. And I key up. All right, my SWR meter is not complaining at all on the transmitter. I look at my power, forward and reverse. At this point on the line, I have no reverse power. I'll even move this around in case it's construction slop. So I'm showing forward power, but I'm not showing reverse. Now, if I come up to this side of the line, this side of the tuner, I should have, if I can get it to couple, I should have a whole bunch of reverse power, but just in this short little piece of space. I'm going to move this a half wavelength back in case I have some bad electrical connections here. That does happen sometimes. Right, remember, everything repeats every half wave. So if it doesn't work there, we can come back here and do it. Okay, so I've got some reverse power showing up now. And that's because that power is bouncing back and forth over this space, but not back here. Because this capacitor, just the little ceramic capacitor that I popped across the line, at the right place and with the right value, that's my antenna tuner. My transmitter's happy, my antenna's happy. If we had a receiver, we would see full scale receive. We're not losing any signal here. Just nothing meaningful at all. All right, so let's switch over to the other mismatch. Let's go back to the 12-to-1.
How are you estimating 12-to-1?
So I did measure, so a couple of ways. So for one, I put it on a VNA. So I know it's about 12-to-1. But that matches what we would expect because we know we can estimate the impedance of this antenna, and we know the characteristic impedance of the line, and that works out as well to about 12-to-1. Okay, so we now have the full wave dipole. This is pretty much our worst case scenario. We're feeding at a very high voltage point on the line. Again, I transmit and my SWR meter is complaining with no antenna tuner. But again, if we had the receiver, we would see that it's only a couple of dB down. Let's see if we can get that couple of dB back. We take a 1.9 picofarad capacitor and we put it 56 centimeters back. And this isn't complaining at all. If we had the receiver working, we'd actually see something really surprising here. We would see gain. We would see our received signal actually go up above where it had been with a resonant dipole. Anybody have an idea about why that would be?
Radiating off more material.
Radiating off more material, and we've built a collinear antenna. So let's click on. So the transmitter's happy, right? I've got my match on there. It's no longer complaining about SWR. The transmitter's fooled, right? Antenna tuners make your transmitter happy. Sure, great. But the receiver is happy and fooled too. It's going to be up about 3 dB over a resonant antenna. So there's a couple lessons here. Reflected power. It's real power. It will radiate if you let it. If you don't burn it up with a big resistor, a big piece of coax, it will eventually radiate. And then, yeah, the collinear thing. Let's click on to the next one. All right, so this is just a demo of just working out as the power hits and reflects and goes back and forth. Let's say we start out with 100 watts. We have an 8 to 5 SWR. I just made up some numbers for this example. We have an 8 to 5 SWR on open line, so it's really low loss, just a couple of copper wires. On the first time through, on 15 feet, we lose 1.3% to heat. You'll never notice that. Okay, so we lose a little bit to heat. 40% radiates. 60% reflects back. We lose another 1.3% of that coming back, reflects again. But you notice, we never, of this 100 watts, a very tiny amount of it, maybe 2.5 watts, gets burned up as heat in this system. But it all eventually gets a chance to radiate. And we get a total of 93.8 watts radiated. We just lose about 6% to heat. Let's go on to the next one. So now we have, again, an 8 to 5 to 1 SWR, but we're doing it with coax in this example instead of open wire lines. So it's a lot more lossy. And again, 100 watts comes out, some radiates, not much. A lot reflects. A lot burns up as heat. We lose 20% on each pass. That's forward and back. So a little bit radiates, a little bit radiates, a little bit radiates, and so on. And in the end, of that 100 watts, less than 50 gets out. All the rest of it just heats up the worms. And click on. So we had this. Let's see if we can mess this up. One of the ways, so you can go by, yeah, who knows where this is going? Open wireline is great. It's very low loss because of the air dielectric. Air dielectric is a big deal. But if your open wireline gets wet, let's say you've got window line, right? Window line actually has a lot of surface area, so if it gets rained on, that's a lot of surface area to hold on to water. And this piece of the demo really needs that receiver, but we don't have it. I key up, and if we could switch over and see the receiver, you would see it be about 20 dB down at this point, just because of this. So remember, we have a really bad mismatch. So we have forward power reflecting. A lot of power is reflecting here. Something like 70, 80% reflects off this mismatch. Comes back here, and then gets re-reflected from this point. So all that power is just bouncing back and forth. But because of our water dielectric from our otter pops here, it gets burned up. It gets turned into heat. And it very slowly starts to boil my otter pops, which means it doesn't radiate. And we lose a whole bunch of power to dielectric losses. And that's why SWR is bad on coax. Because of the dielectric losses of all that power bouncing back and forth, you lose it all to heat. And again, I wish I could show you the signal strength, but don't have the receiver. Let's click on. So yeah, line loss is everything. And again, we got gain from this really bad antenna because it's a collinear. Every antenna is a multiband antenna. Is a funny consequence of all this. If you don't care what your radiation pattern is, you can transmit from pretty much anything as long as you can load it. And loading it is a matter of getting, if your antenna tuner can handle the mismatch. In fact, before coax was common, so pre-war, this is exactly what people would do. They would just throw as much wire up in a tree as they could, and they would feed it in the middle, or if it's a ZEP at close to one end, whatever. But just put as much wire up in a tree as you can, feed it with open wire line, and be happy. Work all the bands, work all the states, get DXCC. Who cares? This stuff is like, your patterns become interesting. You get gain, but that's not a bad thing. Let's click on to the next slide, please. So here's the resonant dipole pattern that we all think about. Here's our situation here, where we're feeding it at the high voltage point effectively on its second harmonic. And we get about 1.6 dB of gain. Because, as you said, we're radiating from two places. We have effectively two dipoles, butt to butt, which makes a collinear. We've made a collinear where we're not paying attention to the element spacing, the end-to-end spacing. And we can keep on doing that. So click on again. We can do it at the third harmonic where you've got bup, 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 fourth, bup, 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 and you just keep on going. And your patterns get a little crazy, but you keep getting gain. And go on again. And yeah, if you can match the load, one antenna does a lot. One wire does a lot. You've got these weird nulls, but you've also got these interesting lobes out there. Have fun, right? And let's go on to the next slide. So our directional power couplers, the SWR meters we have on our desk, one thing that's really important to remember is you will get different answers based on where you measure. Because the SWR meter on your desk is measuring the forward power and the reflected power at that point. So if you were to measure right here, you're going to see all the forward power and you're going to see all the reverse power. This would actually give you an accurate SWR reading from those little units if you could measure it right here. But if you measure it at the other end of 50 feet or 100 feet of coax, you've got all this line loss. You know what you're transmitting. That's going to be pretty accurate. But the return power is going to be, you have to remember that it's subtracted out all this line loss from your return. So,
Double, right?
I'm sorry.
Double, right? You lost energy going out and you lost energy coming back.
You'll lose it going forward, you'll lose it going back, and then every time it reflects through, you're going to lose it again. So if you go, that example we had earlier of the 8 to 5 SWR using coax, if you were to measure the SWR in the shack, it's going to look like 4 to 1, which still isn't great, and we know that's not great, but we don't know how bad it really is. This also means that we can get fooled in other ways. Let's go on to the next one. If your coax is damaged, your antenna system will look great to an SWR meter. If your jacket has gotten ripped open and there's water in the line, so it's now super lossy. It's not just polyethylene dielectric loss, it's water dielectric loss. Ward Silver makes this point pretty often. Measure your system over time, and if your SWR reading from inside the shack is getting better over time, you've got a problem. There's water in your line somewhere. There's no reason your antenna system would get better with age. But it looks like it is because that lossy dielectric with water getting into the line means that you're losing all that return power to heat, which means it can't get measured by your SWR meter. It just won't see the return power, it won't know it's there. But yeah, other ways to have a perfect SWR meter reading. Like we all want a 1-to-1, right? So okay, just transmit into a dummy load. It'll look great. Doesn't mean you're getting out. Use several hundred feet of Radio Shack RG58. Yeah, it'll look great. It's not great. And then yeah, damaged lines, getting better over time, that's a bad thing. Better ways to do it. If you can get an antenna tuner as close to the antenna as possible, if you can get one that's rated for outdoors, it's remote, or if you can just you get it as close as you can and then you just run open wire line the rest of the way, that's going to do really well. So yeah, from the tuner to the antenna, use the lowest loss line you can manage. If that's hard line, if that's open wire line, whatever. Here's the thing, hard line is really expensive. Open wire line, I made some from 14 gauge house wire. I just went to Home Depot and Like just make some spacers from wood or the black drip line hose for your garden, right? That works too. Window line, you can buy that at HRO. It's fine when it's dry. When it's wet, it becomes super lossy, just like this was. And yeah, homemade ladder line, cheap and fun. And that should be close to the end. Yeah, okay. I did add this slide recently. I got criticized for not bringing this up, and it's a fair criticism. There are real downsides to SWR, even if you're not losing signal. Even if you've got a great system that's low loss, high SWR necessarily means high voltage. So if your SWR is really bad and you've got a really big standing wave on here, that voltage maximum can get high enough to arc across the line. That's one reason why 450 ohm line is better than 300, is better than 200, right? The more you can get, the higher voltage that air dielectric will handle. But it can arc across. It can burn through insulators, and you can get other unpleasant surprises. If you touch the line at a high voltage point, you can get, a nasty surprise on your hand. All of this is manageable. But you do need to know it's out there, and you do need to be careful. We use coax because it's really convenient. Getting open wire line through your wall is a real hassle, but it's doable, and people have been doing it. But we have kind of forgotten the advantages of open wire line as a community. And we're so used to using coax, and then we get kind of stupid because we forget what's really happening in our antenna system. So I think that's now the end. Yeah. Bill Hayes, AE4QL, Standing Up for Standing Waves. This is heavily based on his presentation. And then Eric Nichols, KL7AJ, and Joel Hallis from the Dr. Zen have both talked. Actually, the most recent Dr. Zen talks about exactly this, just came out a couple days ago. And that is what I've got. Normally this is about 2.5 hours. It's the whole thing in one. I know that was rushed, and I know we had a little technical problem. Do we have any questions? Yes, Nate.
Very basic. What is that exactly?
You could call this ledger lines.
Where did you get it? How did you?
I made all of this.
Okay.
The 4-to-1 Ballon, that design is right out of the handbook. This is just hobby tubing from, I cleaned out all the hobby shops in town, in Denver, on brass tubing about a year ago. So yeah, it's just 1/8-inch brass tubing fitted together. That's it.
Any particular gauge or?
So the key thing was getting the correct characteristic impedance, and that's just a ratio of conductor diameter and distance between them. So 1/8-inch was easy to work with. So it's a 3-to-1 ratio. So no, that's not right. Anyway, they're 1/8-inch diameter, and they're 1/3 of an inch apart on center. Yes, sir.
What's the on an antenna, for example, like a G5RV, where we have some kind of low loss line coming down from the center point, and coax the rest of the way? What's your feeling on the impedance matching that goes on?
I mean, it works.
How important is it?
So it's an important part of how the G5RV works, right? So one of the things that's important to note here is that your transmission line itself is a transformer. You take a quarter wavelength piece of transmission line, and you will invert whatever impedance you see at one end. At the other end, you'll see the opposite of that. If you see infinite, you'll see 0. If you see, whatever, you see something really high, you'll see something really low. So, so that matching section is taking. You look at all the bands that it's intended to transmit on. You look at the length of your radiating elements, and you can calculate, okay, for each of those bands, what's the impedance is going to be in about this range, some range of numbers. And they said, okay, well, let's find some length of low loss line that will bring any of those bands down to transform that impedance to something reasonable at the other end, something pretty close to 50, give or take 3x, right? It might be 12 ohms, it might be 150 ohms, but you're in that 3 to 1, right? And you just work the numbers and you try different things until you find something that works, and that's what they did with the G5RV. But what that does is it means that your coax, your 50 ohm coax line, it sees when it connects in to that matching section on the G5RV, it sees something reasonably close to 50 ohms. So while you're going to have a bunch of reflections here, you're not going to have a bunch of reflections down here. Maybe 3 to 1, and that's not great, but whatever. Yeah. Anyone else? Normally I let people play with this, but I have to clear out so our next presentation can get in. And yeah, I'll be around for more questions if anybody has them. Sorry that was rushed.